Welcome everyone. It's a very great pleasure to have here today Elsa Teixeira. Thanks a lot for accepting our invitation. Elsa is a postdoc at the University of Montpellier working on tests of lambda-Godel matter, modeling new physics in the dark sector, and testing beyond the standard model theories to address cosmic tensions. Before that, she did a PhD at the University of Sheffield, working on modeling and testing of models of interacting dark energy. Today, she will present Illuminating Cosmic Tensions with a coupled scalar dark sector. Please, you can start when you're ready. Thank you.
Thank you. So first, thank you, Eleonora and Jackson, for organizing and for the kind invitation. So yes, I'm going to talk about how we can try to understand cosmic tensions with coupled scalar dark sector. So hopefully it's clear what that is in a few moments. So this is work that I have done through the course of my PhD and also now during my postdoc in collaboration with Gaspar Poulot, Karsten van der Broek, Vivian Poulin, Nelson Nunes, Saber Hahimi, Yvonne Zavala, and Eleonora Di Valentino. So throughout the course of the presentation, I also have these illustrations from a friend I do public outreach with, which is called Inês Viegas Oliveira. So if you like the illustrations, you can also check her website, and hopefully, if you believe in lambda CDM more than in scalar dark sector, you can also have some pretty pictures to look at. So without wanting to be too extensive, I wanted to just give an outlook of what is the lambda cold dark matter model and why we try to have extensions to it in the context of cosmic tensions. So we know that we have things that are very well established in our standard model of cosmology. So this is what I have depicted on the left. So that could be our basis of our theory of gravity, which would be general relativity. It could be the fact that we assume that the universe is homogeneous and isotropic in its expansion. So this would be the metric ansatz that we take to be the Friedmann-Lemaitre-Robertson-Walker metric. And also the standard model in the particle physics that we have detected and that is very, very well understood, which would be baryons, photons, and neutrinos. Then on the right-hand side, I have depicted everything that is still a bit, let's say, exotic and that we can still not explain properly in the context of the standard model of particle physics. And that would be the way to explain the production of the density fluctuations in the universe and also problems like the horizon problem. So this would be inflation. Inflation in the simplest case can be modeled through a scalar field like the ones I'm going to talk about. This would be the inflaton, which produces this early accelerated expansion of the universe that produces the quantum density fluctuations that give rise to cosmic structure. This cosmic structure, we assume that is made of a dark component, so a coupled dark matter component. So this would be a clustering matter component that is interacting at least very weakly with the electromagnetic sector. This would be about 25%, so we all know this, but also for the late time acceleration of the universe, which we measure and is related with the Hubble tension that I'm going to talk just in a few moments. We assume that this is a constant background energy density that doesn't dilute with the expansion and that can be modeled just as a constant term in the Einstein-Hilbert Lagrangian. So this brings me to the problems that we face now that we, of course, in this community, we all know. So this would be first the Hubble tension. So the Hubble tension would be this discrepancy that we have in the measurement of the Hubble parameter from different epochs of the universe. So one way in which we would measure this would be from CMB, so from the early universe, from which you see here in red that we get a consistently smaller value with very small error bars. Then if we take local measurements, which would in principle be model independent, or at least cosmologically model independent, we see that we have the opposite. So we have values that are consistently on the larger side. So this has been, I put here the values which are the most constraining and they have the smallest error bars, but this has been corroborated by different measurements, and I list some of them here. And so the point that we try to make here is that we have a compilation of measurements that have been made at early times, or at least taking into account physics at early times, and measurements that take into account late time astrophysical measurements. And we find this consistent discrepancy that in principle could be related with the differences in the modeling of the early universe, the late universe, or whatever happens in between. So another tension that is less significant, but it's nonetheless still there, is the so-called S8 tension. And so this also pertains to the measurements of the CMB data compared with other measurements. So this would be measurements at the time of the CMB and measurements of galaxy-galaxy lensing, or also galaxy clustering, that give us a consistently smaller value for these parameters S8, which basically just tells us something about how matter is clustering in the universe. So if we think about the matter power spectrum, it would give us a measure of the amplitude of the matter power spectrum at a particular scale. And we see that when we measure this with the CMB, we get now the opposite. We get larger values taking these early universe measurements. And when we use, for instance, cosmic shear galaxy clustering measurements, we get a consistently smaller value. This has been also recently corroborated by another probe, which is this Rosita, which actually measured an even larger value than the CMB. And so in principle, this is something that could be addressed by having models in which matter is clustering differently. And so we would get different predictions for this parameter, because of course, in this case, both parameters are model dependent. So, okay, saying this, we have these, just putting it in a picture, we have these measurements of the early universe, we have the measurements of the early universe, and whatever happens in between is being propagated using our standard model of cosmology, which is the lambda CDM model. So this model fits very well, for instance, the CMB anisotropies, as I have pictured here. But the point is that we still have 6 parameters that have to be fitted to the data. And we see that if we vary the parameters, even if slightly, this will cause big variations in the predicted shape of the temperature anisotropies, of the spectrum of the temperature anisotropies. And so in principle, this tells us that if we change the cosmological model, we will also change these predictions. And so in principle, we could find a model that still fits these anisotropies equally well, but gives rise to different predictions. So this is true also for the matter power spectrum, and this could help address the S8 tension, for instance. So this is the question we can ask, which is could it be that these discrepancies that we observe are actually a reflection that this propagation that we are making from the early universe, where we measure the sound horizon, up to the late universe, where we actually measure the Hubble parameter, could be discrepant to the physics propagating between the two. Okay, so this brings me to this point, which is how can we formulate beyond the standard models? So this is why I wanted to make this depiction, because then we can think, okay, if we want to form extensions of the standard model, in principle, we should look at whatever is still not so well explained in our model. So one thing would be considering that maybe the late time acceleration is not described by a cosmological constant, and the natural extension to a cosmological constant, which would be to consider a dynamical degree of freedom. And to do so, we could consider let's say, the simplest dynamical degree of freedom, which would be a scalar field. So a scalar field is a natural entity that we have actually already observed. If we think about the Higgs boson, it's a quantity that we also postulate, for instance, for the accelerated expansion in the early universe, so for inflation. And so we could think that we have one of those dynamical degrees of freedom that can also mimic the behavior of lambda, but in fact has a more natural behavior that evolves with the expansion and is not just not diluting with the expansion. So this means that we could have some again dynamical degree of freedom that can more easily adapt to the expansion and could again give different predictions to the observables. So also we have quite strong constraints in how these, for instance, this scalar field could interact with the standard model of the standard model, because this would, of course, cause observational signatures, especially at the galaxy scale. But we don't have these strong constraints when it comes to dark matter, because also since we don't have yet direct observations of the nature of dark matter, we could still postulate that there might be some interaction between the two, or at least leave this window open. This is also the fact that if we have these two dark species, we could envision that they have a common origin. So for instance, they can be manifestations of the dynamics of some higher order, higher dimensional dynamics, such as we have in string theory, for instance. I will come back to this. But the point is that these modified predictions due to the evolution, this non-trivial dynamics in the dark sector, especially in dark energy, could help explain the cosmic tensions. So this has also been a strong topic recently because of the recent data release from DESI, in which it was pointed out that there could be hints of dynamical dark energy, as we see here in this plot. So this is, of course, not a scalar field that is being depicted here. This is just a parameterization of a fluid dynamics for dark energy. But again, this fluid dynamics could be well mimicked by a scalar field, and a scalar field would even have a more diverse dynamical behavior. So what we see here on the plot on the right is that if we have measurements of a BAO from DESI and we combine this with CMB and also with different samples of supernova data sets, we see that we have deviations from lambda CDM, which would be these dashed lines over here, and these deviations will depend on the will depend slightly on the supernova catalog that we consider. So now we could look at the other side. So we have looked at the one side of the dark sector, which is the dark energy side, but we could also look at the dark matter side. The point that I wanted to make is that the dark matter paradigm is not, again, something that we just postulate to solve a little issue and try to glue things together. It's something that is very important for the whole evolution of the universe, and in fact is important since the universe was around 1 second years old until now. So that's a long time, and it has different roles in the different stages of the evolution. So it has a very big role, for instance, in the way in which light and matter were coupled in the early universe. It also has a big role in how they decouple, and then through all the time in which structure is being formed until the present universe, in which we observe, for instance, galaxy dynamics. So in principle, changing the nature of dark matter, or if we assume different particle physics models for dark matter, we would change the way in which the universe is evolving, and also in the way in which matter is being clustered. So again, since we still don't have a particular dark matter paradigm, what we know is that the dark matter can span a very large mass scale. So depending on its nature, it can go from, for instance, we see here on the right, the order of 1 to the 30 solar masses, if we think of primordial black holes, to something like 10 to the minus 22 EV, if we consider ultralight dark matter. And so its nature, and it's also the way in which it clusters and which it interacts with the other components of the universe, will be very different depending on its mass. So having this very large range of parameter space means that if we want to probe different natures of dark matter, we will also need different probing strategies. And so this also means that modeling its behavior is quite important so that we can look for the right signatures. So then we see here on the left, so when the mass of the dark matter becomes small enough, so we say kind of below the EV scale, the dark matter starts to be bosonic, starts to be non-thermal, and we can describe it efficiently by considering a classic field. So this means that we could still treat dark matter as a scalar field as well. It would still be a dynamical degree of freedom, even if it has to satisfy specific properties that we know dark matter must have. So another thing is that recently there was also this observation of the stochastic background of gravitational wave using PTAs, and we know that ultralight dark matter could also be, for instance, an explanation for at least a part of this stochastic background. Okay, so now if we try to bring the two things together, we could envision that we have some fundamental description of these two scalar fields. So what I have written here is just the most general Lagrangian, in which we have just some term depending on the scalar field. We can have more than one, so depending on the scalar fields in the theory, and also its derivatives, which are described by this parameter x in this px of phi. And the fact is that we can have multiple scalar fields. This term can be canonical if we have classical scalar fields, but it can also be non-canonical, so we can also have more complicated features. And it's common that in more fundamental theories, we consider two scalar fields that can even have a fundamental origin, a common origin. And this common origin could help explain, for instance, a common origin for the dark sector, which, as I was saying before, it's the case, for instance, in some cases of string theory, or even brain models, or some kind of models in which these two scalar fields have a geometrical interpretation. So then if we have two scalar fields, we can write again two kinetic terms, one for each scalar field, which you see here as phi and chi. And then we would have two different ways to couple them. So we could think that one of the scalar fields is actually this dynamical degree of freedom that can enter, for instance, in the metric. And this means that also if we have this dynamical degree of freedom entering in the metric, we will have curvature of flat space that is associated with curvature as in the Ricci scalar curvature that is associated with the presence of this scalar field. So this is what we see here on the bottom right, given in terms of the derivatives of this function f, which would be this function appearing in the Lagrangian. So when we do this, we can have some sort of coupling between the two scalar fields. So this coupling can come either from a kinetic interaction. So either we have a function of one of the scalar fields coupling to the kinetic term of the other scalar field. And this can come through this function f, which would be related again with the curvature, but is the same as in conformal transformations, if this is something that you are more familiar with, in which we can transform different theories of in GR plus one extra degree of freedom, and we can transform between them, taking different frames depending on whether it's gravity that is non-minimally coupled or matter. Another, let's say, simpler thing in which we can do this, because then we would be coupling just the scalar fields to themselves without considering the kinetic terms, would be to have a potential interaction, which is the second term, which is just saying that we have two scalar fields that are evolving in a common potential, which is what happens, for instance, in models of inflation, where we have one auxiliary field that helps the inflaton decay. So this is a very general approach, in which we would have, let's say, a dark Lagrangian for the two scalar fields. And when we do this, we see that we naturally obtain a coupling between the two fields. So we would have the choice of the rules of each scalar field would have to be driven by phenomenological considerations, in the sense that we know that one of the scalar fields will have to behave like dark matter, the other one like dark energy. So they need to have specific properties. And in the models I'm going to talk below, for instance, one of the properties that we look for in dark matter is to have some kind of shift symmetry that can be broken, and that can lead to dark matter behaving in a certain way in certain scales of the universe, and then having this shift symmetry be broken and decay into a minimum of the potential. So when we do this, we obtain this coupling between the two scalar fields, and in particular, one very general way in which we can write this, which we have shown in this work that I put here, the reference, is to show that we can write this in terms of an interacting vector, in which when we do so, we kind of, in some way, at least in the background, lose track of whether this interaction came from this kinetic interaction or from this potential interaction. And the only way to distinguish between the two would be to keep in mind that these two functions have actually a very different meaning in the Lagrangian. So this could help us understand whether we can distinguish between actually different kinds of interactions, especially first at the background and then at the perturbation level. So now to give a concrete example of this. This is a work we have studied in the past. So with, if I go back, with Karsten van der Broek and Gaspar Boulot, which is basically a model inspired exactly in what I was saying before, so in hybrid inflation. So in this hybrid inflation, we will have this kind of potential. So I don't think I can point, but if we are coming from the phi direction, we see that we have a scalar field that is slowly rolling in the phi direction. So from 4 to 0 in this illustration is rolling in this potential. The field chi is frozen around 0. And then once the field phi evolves enough and it approaches its minimum, so around the 0 or approaches a critical value, there will be this symmetry breaking that I said before. And then the scalar field chi would fall into the minimum of the potential, either in one side or the other, and will remain oscillating in the minimum of this potential. So in hybrid inflation, this is used again in the case that we have an auxiliary field that helps give rise to the end of inflation. And in this work, what we have done is consider exactly the same potential, but envision now that one of these scalar fields, instead of being an auxiliary field, is dark matter, and the other one is dark energy. So now we have this kind of potential interaction that I had just shown before. So we have a common potential for the two scalar fields. This is a very general potential. You see that it has 3-4 parameters. But we have to analyze them and try to extract the fundamental properties of dark energy and dark matter so that we can realize dark energy and dark matter. So the first step would be to know that the second derivative of this common potential gives us the mass of each of the scalar fields. And then based on this, we can impose dynamical constraints in order to be able to have this, for instance, oscillatory behavior for dark matter. So when we did this, we concluded that we needed all the other terms to be suppressed. And in the end, we have just this simple potential, which is basically just a constant scale. So this V node plus some quadratic term in each of the scalar fields. So then we see that exactly when we do this, we have this parameter G, which is the coupling parameter, and we have the mass of each scalar field depend actually on the value of the other scalar field. And now we can start making this dark matter, dark energy property association. So in general, what we would like to have is a dark matter scalar field that is oscillating in a potential. So it's oscillating around zero pressure behavior for dark matter that we usually look for. And we have a scalar field that is slowly rolling. And so it's also in some way mimicking throughout most of the evolution the behavior of a cosmological constant and then only evolving in the late universe to explain the accelerated expansion. We know that the field should be oscillating. Actually, this would be larger if the mass is larger than the Hubble radius. And so we can also impose this such that the mass of the dark matter field is large enough that it's oscillating, while the mass of the dark energy field is small enough that it's slowly rolling. Another thing is that we know that the dark matter has to be approximately pressureless, as I was saying, and so we can make this approximation that its energy density is actually given just by the mass squared times its value squared. If we again compare with the fact that dark matter has to be the dominant component of the universe at some point, so it has to dominate over the Hubble scale, also while it's oscillating. We see that also the field must be slowly rolling. And so in the end, what we find is that the scalar field has to be, the scalar field phi has to be actually larger than the Planck mass, which again, the sign is also wrong. So it should be larger. The field must be larger than the Planck mass. When the field is smaller than the Planck mass, in this case, the chi field will stop oscillating. The fields will settle in this minimum of this potential. And so actually the accelerated expansion would end in the future and we would just have this vacuum solution. So this means that in this model, it's actually the dark energy domination is actually a transient period of the universe that we are experiencing now, while the two scalar fields are evolving. So then what we can do here, which is then a powerful tool when we deal with scalar fields, is to have some kind of fluid approximation in which we look for the dynamical behavior of the scalar field and try to average it out over the oscillations so that we can have a non-oscillating stable solution that we can model as a fluid rather than as an oscillating scalar field that can also be especially computationally very heavy. So what is usually done, which is the same that we do, for instance, in quantum field theory, is to take what is called a WKB approximation. So this is just taking this kind of ansatz for the scalar field in which it's evolving in a sine or cosine solution that models this oscillation. And then we can keep averaging out instances of the presence of the scalar field. So chi dot, chi squared, whatever, so that we can go back to the definition of its energy density and its pressure and rewrite it in terms of fluid quantities. So when we do this, we have this approximation. So we see that rho chi on its average behavior is evolving as a function of phi. So this would be the second box on the right. So it's evolving still with a behavior that is reminiscent of its decay as a to the -3, but we have now a term that is giving us like a measure of the evolution of the dark energy scalar field. So it's telling us if the dark energy scalar field is evolving a lot compared to its initial condition. We will also have larger deviations from the a to the -3 behavior of dark matter. So with this, we can write actually the continuity equations, assuming that both scalar fields can be described as perfect fluids and with a fluid description for dark matter. So we see here that what we obtain is the usual continuity equations, just that for raw dark matter, we have the pressure being 0, but we have this conservation of the energy by having the terms on the right-hand side of each equation with an inverse sign. So what this tells us is that we actually have some kind of coupled dark energy model in which the coupling is given by phi dot over phi times the energy density of dark matter. One interesting thing is that if we integrate out the behavior of the dark energy scalar field, we see that during the matter-dominated epoch, according to the evolution of the scale factor, actually the energy density of phi is evolving proportionally to a to the -3. And so we see that in this case, during the matter-dominated epoch, the scalar field phi is actually scaling with dark matter. And this was a feature that we found, and that then we showed that is actually, this is the only formulation that you can make in which you have this kind of particular behavior during the matter-dominated epoch. So this means that in some way, this rho phi will be contributing as an effective dark matter component during the matter-dominated epoch. So then what we did after, so with, again, Gaspar Poulot, Karsten van der Broek, but also Eleonora and Viviane Poulin, was to look at how to constrain and understand this behavior, especially this dark matter contribution coming from the scalar field. So as I was saying, in practice, we have some, what could be reformulated as a couple quintessence model, just that now this coupling is very unique in the sense that we don't actually have a coupling parameter. So usually we would see here on the right-hand side of the continuity equation, we would see a rho chi, we would see a chi, xi, or a beta, or an alpha, or whatever we want to call it, but we would see a coupling constant. So here we don't have a coupling constant, we have just the scalar field itself and its derivative. And what this is telling us is that actually the coupling constant will be the initial condition of the scalar field. So this means that actually the initial condition that we give to the scalar field straight after inflation, let's say, or during the radiation-dominated epoch, will be what will determine the value of the coupling. So this is not straightforward because, again, it's good we have just a one parameter extension of lambda CDM, but in the same way, we are playing with two different things. So we are playing with the coupling, but we are also playing with the nature of the scalar field itself. So we can, for instance, not set this initial condition equal to 1 while also setting its velocity to 0, otherwise, both to 0, I mean, otherwise the scalar field would just not be present. So we have to be very careful with the balance of the two. On the other hand, it's a very self-contained dynamics, and it's also a very self-adapting dynamics that can be easily tuned just by the initial condition of the scalar field. So as I was saying before, the fact that there is this effective dark matter contribution coming from dark energy, which can be rewritten as we see in this box, this yellow box on the top right, is that we can also gather everything that is not effectively evolving as dark matter, as decaying as a to the -3 in a single component that we can say it's the effective dark energy component. This is something we can do at the background only, just to assess the deviations that are coming from the coupling, kind of assuming that dark matter is still decaying as a to the -3, and we shift everything else that is non-standard to this effective fluid. So when we do this, we see that depending on the value of the scalar field, we will have this different effective behavior that will also reflect how fast or how slow the dark energy component is evolving towards a cosmological constant-like solution. We see also that we have this extra contribution coming from the dark matter component, the non-standard behavior of the dark matter component, which will be larger for larger values of this coupling parameter, which is this inverse of the initial condition. Okay, so then when we compare this with data, so here we have taken the CMB Planck 2018 data. We have also taken its combination with the DESI BEO data that I mentioned in the beginning, and also with the Pantheon Plus supernova catalog with and without the calibration coming from SHOES. So since this is again a one parameter extension model to lambda CDM, this parameter can also not be very deviating, otherwise we would have a very large evolution of the dark energy scalar field, and it would dominate to Worley. We see that if we take, for instance, just the CMB case, we have constraints that are very, very similar to the lambda CDM case, just with larger error bars, but the behavior is overall very similar. On the other hand, when we add, for instance, the DESI data, we see that the DESI data helps break the degeneracies that we had otherwise by using just the CMB. And this data is also much more sensitive to the dynamical behavior of the dark sector at the late times, just as I showed before for the W naught WA case. And in fact, what we see is that this DESI data, if we look at this bit that I have highlighted over here, tries to push the value of the physical matter density towards smaller values, which is not so easy to do with lambda CDM, because then you would be degrading the fit to the CMB, while if we do it for instance, this hybrid model, we manage to have this negative correlation between the physical matter density and the coupling parameter, which is this 1/5. This happens because this dark matter component has this extra contribution coming from the coupling, and so can actually decay faster than it would otherwise in lambda CDM. So initially we would have this matter density that is slightly enlarged than what we would have in lambda CDM, but actually at present it has to be smaller in order to compensate this behavior, and so we have this decreasing correlation. Another point that I wanted to make is that with the DESI data, we actually have a detection of the coupling parameter. So this would be, maybe we can see it even here, would be, for instance, the green contour that we see over here, and we see that actually we have the value of this coupling 1/phi being non-zero at more than 1 sigma. This additional contribution that we get from the dark matter effective behavior is coming from this coupling and from this effective fluid, and we see that is especially favored when we add the DESI data. And this is in line with the fact that the DESI data again found preference for this dynamical dark energy. That's just that it was phantom dark energy, but we see that here, instead of having the phantom component, which would be in this plot, the DESI best fit prediction would be this dashed yellow line. In our case, we have a component that is non-phantom, but this, let's say, phantom detection is actually a coupling detection. So it would be equivalent to a detection of this 1/5 being greater than 0. Having the advantage that with this scalar field, we never have actual phantom behavior. We have just this coupling between the two components. So then we see here the correlation of the coupling with the Hubble constant. We see that there is a mild alleviation of the Hubble constant, in the sense that depending on the data set that we consider, we can approach these bars that I have depicted here around 73, which are the Schu's prediction for the H0 value. So we see that with CMB, we could in principle approach this value, but still there's still some leftover tension. So we still don't exactly solve the Hubble tension in the sense of having these contours being compatible with the error bars. This is especially relevant when we add the Schu's calibration, and we see here that we have a big increase in the chi-square when we go from lambda CDM to the and from not having the Schu's calibration to having the Schu's calibration. And in fact, we have also support from the Bayesian evidence that support for the hybrid model over the lambda CDM model. But just when we add the Schu's calibration, otherwise we have just very small evidence, and so it's quite inconclusive. And what we remark here is that actually when we look at this QD map metric tension, we see that there is still this residual tension that is hidden in the fact that we do manage to fit the value of H0 better, but we have worsened the fit to both Planck and DESI while doing so. So this is an example of how we can use the scalar field models to try to mimic this behavior and possibly alleviate the H0 tension and move towards the goal of actually solving it with the dynamical component. So then in these last few minutes, I wanted to show just another example of this kind of models. So this is also work with Gaspar Pullo and Carsten van der Broek, and also with Nelson Nunes in Lisbon. And this is the same kind of thinking, in which we have two scalar fields, but based on the successful models of Axion-like dark matter. So on the spectrum of the ultralight scalar fields that I had mentioned in the dark matter mass range. So these models are very successful in the literature, in the sense that we have, again, dark matter behaving as a scalar field. This scalar field has this very big oscillating behavior, so it's evolving in its potential. This oscillating behavior can again be mimicked by a sine-cosine solution. And we see that we can take this fluid approximation that I have just mentioned for the previous model in order to mimic very well the behavior of these oscillations. So we see here for the energy density in the bottom right plot that we can have this approximated solution in orange that mimics very well the exact solution despite not having these oscillations. And you see also that these oscillations start on the top right panel. These oscillations, the onset of oscillations is given exactly as we were saying before, when the mass of the scalar field is larger than the Hubble radius. So this is just an illustration to say exactly what is happening, which is if we have two scalar fields, we would have this kind of Axion-like potential, which is also this top hat potential, in which we see that we will have some scalar field that has, again, this symmetry breaking. So was on top of this hat, has this symmetry breaking, falls into the bottom of the potential. And then because there are these small wiggles in the bottom of the potential, it keeps oscillating around the potential. And this is what generates these oscillations in the scalar field. So again, this leads to modified dynamics in the sense that even when we average out, we don't have these oscillations anymore, but we have the remnants of these oscillations present in the averaged quantities for the fluid approximation. So if we rewrite everything as a fluid approximation, we have something very similar to what was there before. So we have the equation of state parameter has to be on average 0, and we get an uncoupled continuity equation like the pink one on the bottom, and we can average out the solution of the chi dark matter scalar field in order to rewrite it as a fluid. If we take this to the perturbation, so this is a very well-known result for Axion-like dark matter. If we take this to the perturbations, we have we didn't have changes in the averaged equation of state parameter, but we have a scale-dependent change in the average of the sound speed of the dark matter. This will enter directly in the computation of the matter power spectrum. And so since you see here for this expression in pink that this sound speed will now be dependent on the scale, so on k, this means that when k is much larger than the mass, we will have this suppression to the matter power spectrum that we see here on the right. So this gives rise to a suppression depending on the mass and depending on whether the whole of the dark matter can be made of this Axion-like component. We have this suppression on the small scale, so on large k, and this is a very well-known feature that can help address the S8 tensions. It will help achieve smaller values of this amplitude of the power spectrum at the scales that are probed by this S8 parameter. Yeah, so this is just a summary of what I have just said. And the idea that we had was to try to do the same, but again, with a coupling between the two components. So going very quickly through this, just to a lot of Lagrangian details, but the point is that initially we were trying to mimic these couplings that are very well known for addressing the Hubble tension, which is this expression in pink. So this Q proportional to H chi xi rho phi. So it's known that this dependence on rho phi can arise and help with the Hubble tension, but in fact, this cannot arise from the type of models that I just showed before. So the type of models that I showed before, where we have this coupling being mediated by the dark energy scalar field, always originate a dependence on the rho dark matter in the coupling. And so what we thought was to do the opposite, in the sense that let's think whether this dark matter scalar field can be mediating the coupling instead. So this is what we have done in the same kind of approach as before. And in this case, we end up with a model that is a combination of both this kinetic interaction and this potential interaction that I mentioned in the beginning. So we have something that is multiplying the kinetic terms of the dark energy scalar field and also the kinetic terms of the dark matter, the potential term of the dark energy scalar field. So this is what you see here on the bottom. So on the first panel, on the yellow panel, we see the action for dark matter, which is just standard. It's just a canonical kinetic term and the potential. In the second one, we see the Axion-like potential. So it's just a mass squared potential. And then we see this rewritten metric coefficient, which now depends on the dark matter scalar field. So again, when we do this, you see that for the pink, the box in the bottom, we have dependence of these metric coefficients in the kinetic term and also a squared contribution in the potential term. So we have a kinetic plus potential kind of coupling. So then we can do a very similar formalism with all this averaging of the scalar fields. So I spare you from the details because these are quite horrible equations. But in the end, we have these functions that I just wrote here generically, which we wrote as these Q0 and Q1 functions that will appear also in the background. So we have these Q0 functions, which will be functions that don't really depend on the scalar field. And then we will have more complicated functions that depend on the scalar field and need to be averaged out. So when we do this, we get a modified Klein-Gordon equation that depends on this Q0, while the effective mass depends on this Q1. So we have these two functions appearing. Then again, we can take this effective fluid behavior. Now we have to do this WKB approximation in which we take the average of the scalar field, but we take the average over the oscillation solution that we already had for the uncoupled case, plus the extra terms that will come from this coupling. So these extra terms can be approximated at the background as this Q0 over the effective mass that again depends on Q1. So this will have a lot of complicated terms laying there that we can average in order to get the fluid approximation behavior. So here, just to show what we obtained that is different from the uncoupled case is that now the average of the equation of state parameter at the background is no longer 0. So it's actually a function of all these parameters that you see here. So the function of the Q1, Q0, there's even rho phi appearing there. The point being that this can be very close to 0 for a long time. And of course, this is very exaggerated in this plot over here, but it might be slightly positive during most of the evolution, while at late times, it will take on negative values, which again are very exaggerated in this picture, but this is meant to highlight that we can have slight deviations from the equation of state being 0. Then when we do this for the equation of state, we get something that is for the sound speed, we get very similar behavior. So we get now an extra dependence. So we get the scale dependent terms that were already there for the normal uncoupled axion. And then we have these two terms that depend on the coupling. So this means that in this case, not only will we have the suppression for large scales, but we will also for small scales, but we will also have an overall suppression or enhancement that depends on the value of the scalar field. So this in principle could be relevant for the SA tension. And we see again that we have this suppression of the matter power spectrum. And when we look at the constraints, we see that actually this has an effect on the SA parameter. So here we are showing these are chains that are being run by Gaspar at the moment. And what we see here is that we have made a first approximation just to see the behavior of the model, because since I said these equations can be quite intricate, in which we assume that the dark energy scalar field is effectively behaving as a cosmological constant that is still coupled to the dark matter scalar field, but again, first approximation is coupled only through that Q1 term and not through the term that will appear in the perturbations. So in this case, we still get the Axion-like sound speed, which is scale dependent, just that we have a slight different contribution at the backgrounds due to this coupling, also in the perturbations due only to the Q0 coupling. So when we do this and we compare it with the CMB data, now this is the data release, the fourth data release, the recent data release from the likelihood for Planck, and we combine it with the same data set, so with DESI and with the supernova in shoes, we see that actually there is this correlation between the coupling term and the S8 parameter that we think would be even more pronounced once we include the full dynamical behavior of the scalar field and also the Q1 component. So again, we see that this could help address the H0 tension, even if for the S8 tension, even if for the H0 tension, in this case, it's completely degenerate. So we see that there is no effect on the H0 tension. And this again is related with the fact that we are considering a cosmological constant. And so this coupling is not modifying the background dynamics. So this is what I wanted to say, just to say that we have these tensions, these cosmic tensions that we all work on, and try to understand how changing or looking further for the behavior of the components that we still don't really understand the nature of. So this would be the dark sector, looking for the nature or natural extensions to the dark sector beyond lambda CDM could help us understand the origin of these tensions. So then I have shown you two models. So one model in which we do a late time scenario that is based on hybrid inflation, in which we have this coupling between the two scalar fields leading to the symmetry breaking. We saw that there is this suppression of the matter density today that can help alleviate the cosmic tensions, even if not solve them completely. And then another model in which we have an Axion-like behavior for dark matter. And we see that there is a suppression of the matter power spectrum at all scales, but mostly on small scales that could help definitely with the S8 tension and possibly with the H0 tension once we consider the full evolution of the model. So this is all I had to say. Thank you so much for your attention. And just to say again that if you like some of these illustrations, you can find them in the website of my friend. Thank you.
Thank you so much. Very nice talk. Masoud, do you have a question?
Yes. When you put the interaction of two scalar fields, you use the usual derivatives, right?
Mm-hmm.
So it violates diffeomorphism invariance of the gravity. But probably if you would put there, in principle, you should put the covariant derivative. You agree with this? In order
Yes,
not
absolutely.
to, you agree with this?
Mm-hmm.
Do it. So probably it does not matter if you put in kind of approximation, it would put covariant derivative in the interaction between the two scalar fields. So you have to do a kind of approximation. Probably it would not matter if you would do really the covariant derivatives. Do you agree with this?
Yes, so I think it would matter only if the scalar field was non-homogeneous. So if it didn't depend only on time, maybe it would matter, right? Because you would have the possible extra terms coming from the space component Christoffel symbols. Do you agree?
Yes, but you
Yeah.
have to do an approximation because otherwise, in principle, you should not violate gravity. It means diffeomorphism of the usual gravity in your action.
Mm-hmm.
This capital X. This capital X has to be, in principle, the covariant general relativity covariant derivative rather than usual derivative you have put. So
Yes, I agree.
here there is a approximation probably one can justify. Do you agree with that?
Yes. Mm-hmm. Yes.
And then another question, can I ask? When you say that the energy momentum tensor is conserved, do you use the usual derivative or covariant derivative?
Covariant. There it has to be covariant actually. Mm-hmm. So in this sense, I agree absolutely with you that the other one is also covariant, and it's kind of an abuse of notation to have written it like this, right? Because it's already knowing that it's going to be the same. but in principle, it should be the covariant.
But you have you checked it, because you see a piece of the term which enters in the energy momentum tensor has no covariant derivative due to the dark matter one. You have checked that covariant derivative will make it zero, yeah? Because
Yes,
it's a little
absolutely.
bit here,
Again, if it's
a little bit
homogeneous.
it is inconsistency, a little bit it looks a little bit inconsistent, because a part of the action is not
Covariant.
invariant, covariant, and then the energy momentum tensor has two pieces. One is covariant, one is not covariant. So it is a little bit strange, sounds to me a little bit not clear that whether a covariant derivative of the energy momentum tensor is here really zero. Anyhow, it's good to check that point.
No, I agree with you. And again, it's a complete abuse of notation, so it should be covariant here.
Thank you.
Well, in the same way that it's here on the dark box.
Yes,
or the
thank you.
yellow even. No, thank you.
Thank you. Sayantan?
Great talk, actually. I'm also working a little bit on scalar field theory, dynamical system, lots to here. So I have mainly the first question is that when you take the interacting term, that works as a viscosity, right? I mean, it is proportional to h phi dot zeta, something like that, right? The Q term. Yeah, so I'm asking that, could you comment on the zeta? Like, I mean, if you do the Bayesian analysis, etc., from the observation, like what should the zeta parameter would come to? Because when yeah, I mean later actually when you took the entropy, Q proportional to phi dot 8 zeta.
To phi dot 8 theta.
Q equals to yeah, that thing, last line. Q proportional to 8 zeta rho phi. That is the interacting term. And zeta would affect as a somewhat of a viscosity term because it comes with a h, like the drag term, etc. So I'm asking that, could you comment on the zeta? Because whatever I see such a term in typically like interacting or bulk viscous cosmology, etc., the parameter of zeta really runs wild, because you can always choose an arbitrary zeta and always fine tune it to you put it in the Bayesian analysis. On the other hand, if you just look from the cosmological point of view, I mean, zeta cannot be too much because it is like the off-diagonal term, etc. So I'm just asking, could you comment on the zeta's order of magnitude? I mean, it seems like it is a free parameter which you can always beat it to, say, I mean, like made it into Bayesian prior.
Yes, so the order of magnitude, I don't know if I have here a slide, let me check. But the thing is, you can usually, yes, constrain this mostly based on the perturbations, right? Because what will happen is that you will have this Q, just like you were saying, depending on the model, this Q will appear in the perturbed continuity equation and in the perturbed Euler equation, right? And when this happens, you will have a friction term and you will have a fifth force term. And you know, for instance, that these terms cannot be they have to be of the percentage order when you compare with the gravity itself, right? So it cannot be, otherwise we would observe these very strong gravitational deviations. And this is why it can seem arbitrary, but you will constrain them with the data. And this is exactly what the data is constraining, right? The amount of deviations that you can have from this gravitational behavior. So of course, this will be very dependent on the model. And but this usually has to be, let's say, of the maximum, I would say 5% deviation. But this is a very depends really on the model, right? Because you can have effects that are compensated between each other.
And the second question is that you took like the quantum type of scalar field, because there are two scalar field, one is real and one is complex, typically comes in, say, string theory, like DBI field, etc. I'm just asking that, could you comment on when you did the conformal transformation? Basically, you went to Einstein frame to the Jordan frame to get a exact scalar field, right? Yeah, but I'm asking that for one single scalar field, we already know the answer. For example, Stravinsky gravity, we can always get a scalar field corresponding to that. But for quantum-like scalar field, like what you have taken, say V plus I psi type, what would be the corresponding Einstein frame? Because in Einstein frame, you only need one FR, right? So if you do a conformal transformation with respect to phi, you will get a f of 1R, But on the other hand, if you do a conformal transformation with respect to I chi, you will get something F2R. So it is not clear to me like how the inverse of the conformal transformation works. I mean, I understand in the Jordan frame it doesn't matter, but if you want to go to Einstein frame, what should be the corresponding, I mean, like the geometric Lagrangian?
So I
that
think
is not...
that's actually a very good question. I think it depends
Yes.
on which scalar field is mediating this this conformal transformation, right? It's just that it's not as straightforward, because now you would have two scalar degrees of freedom, right? So you would use one to do the transformation, but the other one would remain there, right? So you would in some way have
Actually, I'm also not sure that whether you can find a single conformal transformation, because for one scalar field and FR, their conformal is the I mean, the Weld factor you can always do. For two, I'm not sure even there is a single conformal factor which can kill the both bird. I mean, that's what I'm got little worried, because I mean, like, what should be the geometric equivalent of such a Lagrangian? I mean, what you have gotten in the second.
Yes, so this is assuming that there would be a geometrical equivalent, right? Which might just not be, or might even not be invertible, or even if it is invertible, it might be that you get both couplings being non-minimal, right? That you'll have a non-minimal coupling to gravity, but also to matter. I think the only way in which I see that this would work is if you have exactly the case that I showed here of the conformal case, in which this function g has to be somehow related with the function f, so that you have the two being related, and then you have one unique function. Then of course you can invert. If they are different, I'm not entirely. I actually don't think you can do it without you cannot do the Einstein-Jordan frame. Like you can still change between frames, but you have the non-minimal coupling anyway. You would not be able to get rid of one of the non-minimal couplings, I think.
Yeah, I mean, this one is fine. I mean, that was is from vanilla inflation, you are going to the FR corresponding, but that's what I go worry. If you want to take phi and chi both, I mean, also chi has a I in front of like a complex number I. I'm not even sure like what would be the corresponding FR gravity corresponding to that, like the physically Einstein frame.
Yeah, I agree. I'm also not sure, and I'm not even sure it's possible. That's what I mean.
Yeah. Okay, ma'am, a very good model. And maybe just a small, tiny question. I mean, it is something I am not aware of, so pardon my ignorance. But I'm asking that you are working with the speed of sound as some perturbation as a to check the phenomenology. So I'm asking that when you are taking, say, quantum, like say complex scalar fields or something like which are tachyon-like scalar field as a effective string theory or something like that, some heterodyte. So the speed of sound might not always be even positive or even real. I mean, it could very well come out to be negative. For example, if you take phantom scalar field, the C square would be just plain -1. In fact, even it is less than -1 for, say, just tachyon scalar field. So I'm just asking that, is that, I mean, such a speed of sound good measure? Because most people, I mean, even in Zeldovich's book, he often says that the speed of sound, we have calculated the CSS square formula as d dot by dp, assuming the perfect fluid approximation. So if we are going towards the, say, stiff matter limit or the phantom limit, I mean, the formula CSS squared is dp by d rho is itself not valid. So that's what I was commenting. I think in Zeldovich's book, this comment is needed that CSS squared formula, the dp by d rho, is itself derived, assuming that it follows the standard Euler equation, right? And for phantom like one, I mean, this formula speed of sound, the perturbation itself, we do not know, like what should be the equation of state, etc. Or even worse, it would come out to be negative, right? I mean, for phantom, you can clearly see that it would come as some -1.1 or 1. So that's why, could you just comment that is the speed of sound is a good quantity to check? I mean, I understand phenomenologically it is very important because you want to see the anisotropy of Bow or something like that. But in this context, could you just comment on that if I,
Yeah, of course. So I think that for the speed of sound, you will have to check for instabilities, just like you were saying, right? You would have to check that the Hamiltonian is bounded from below and all of these things. The thing here, which is why it works as well, is that here, when you do calculate the speed of sound, you are doing a fluid approximation, right? So it's you are not looking for the speed of sound of the scalar field. You are looking for the speed of sound of this approximated behavior. And so in this sense, it is you can show that it is well defined, but I agree that if you have also more complicated dynamics, in principle, you would have to check. And it's also, to be fair, it's something that can be checked here as well.
Yeah.
But yeah, I agree
For example,
that this
in this
is
formula
an
also, like
important.
we will get, Yeah, sorry. I'm asking even in this formula also, we'll get strictly -1, even less than -1 if we just take the phantom field, right? I mean, if I take
Yeah.
Lagrangian as plus of this plus of V phi, we'll just get less than -1. So that is a complex behavior itself here. I mean, complex behavior is not a problem. It would probably indicate a decaying mode. So that's what I'm asking, that the speed of sound is a good characteristic if we are using some effective exotic scalar field. I mean, I understand people do it, but it was a question of mine. Yeah.
Yeah, exactly. Which in this case is fine because it's a canonical scalar field, but you still have to check it for the coupling, for instance, because it could be that, especially if this coupling had some kind of kinetic dependence, then you could not guarantee because this kinetic term could even cross 0, right? So I think in that case you could not. You still have to check. That's what I mean. Yeah.
Thank you, ma'am. Very nice talk. Yeah.
Thank you. That's very nice questions. Thank you.
So let's take Elsa again.
Thank you.